Okay, just sorting out the technology now. Thanks very much for the invitation. It's a pleasure to be down here in Tasmania and talk very briefly about the physical basis for how the climate is shifting. And I'm just going to address one question here is how fast is the Earth really changing with a focus on climate? Because that really is the sort of thing we need to know to understand what species and ecosystems face as they try to deal with this issue. So I'm going to go way back in time. This is about a 400,000 year record from Antarctica. Just look at the the red line in the middle. That's temperature over 4 glacial interglacial cycles. And of course, ecosystems have survived that quite well because when you look at the time frame here, it's, oops, how do we go back? There we go. When you look at the time scale here, it's actually quite long. So one of the things I want to point to a little bit later is this line here, which is the last ice age coming into the warm period. Look how steep that is, because I'm going to compare what's going on today with what ecosystems went through back then. So I want to home in on this last bit, the last ice age, and this little bit here, which is actually very important for what we're going to talk about. So if we do that, that's the last 100,000 years. See, the climate's extremely erratic during the ice age, but look at this last about 11,000 years. That's called the Holocene. And that really is the baseline by which we measure the climate change that we're experiencing today. Because this is an unusually long warm period, it should last for another 20 or 30,000 years without human interference. That's the baseline a lot of our ecosystems and species have been operating on for about the last 12,000 years. Well, this shows you an example of what's happening to that baseline now. And again, I want to talk mainly about climate. There's surface temperature there, which I'll focus on. But one point I do want to make in passing, it's not only the climate that's shifting. A lot of other things are shifting really fast. Here are the 3 famous greenhouse gases. There's CO2. But nitrous oxide and methane are also changing extremely fast. The ozone hole, of course, in the southern high latitude plays a role because of the extra ultraviolet radiation. Ocean acidification is sweeping up probably as fast as it's gone for hundreds of millions of years, and marine species have to deal with that. And then we look at direct human impacts through aquaculture, through fertilization, and through direct modification of the terrestrial biosphere. So species are coping not only with the really rapidly changing climate, but also with many other changes in the biosphere that are directly due to human activities. One of the most important ones, though, is in the biosphere itself. This is actually a fairly unusual place on Earth. It's Arnhem Land, but there aren't many places left which are pretty much in the same state they were at the beginning of the Holocene. Much more common nowadays are scenes like this, which are very heavily modified systems by humans. And so it becomes important because when you look at the rate at which climate is changing, species have to try to move through landscapes like this more often than they can move through undisturbed landscapes. So let's return to the climate then. These are the latest global mean temperature charts with 2015 at the top there. It was the hottest year on record globally by a long way. But the important part is it's part of a much longer trend. So if we look particularly since about 1970, we can really see the human impact on the climate from that point onwards. So now we're going to try to put this in the perspective of that longer term background climate that I showed you earlier. So that's the last 2,000 years of that 11,000 year Holocene period. And of course there's natural climate variability. You may have heard a lot of people talk about that. But when we look at natural variability, you can see it here. It actually acts within a well-defined envelope that is due to the orbital forcing of the climate by the Earth's orbit around the sun, its obliquity and its precession. So we know what that's going to do. So that's what it looks like for about 2,000 years. Again, this is what species, this is what ecosystems are used to. Here is the contemporary climate change, that one I showed you on the previous slide, put on the same time scale. So again, from about 1970, which is just about here, you can see how rapidly it's sweeping up, well outside the range of natural variability. What we can do now, though, is put the projections for the future. Many of you will have looked at the IPCC reports and looked at the projections of anywhere from about a 2-degree temperature rise up to 4 or 5-degree temperature rise. And a lot of people look at those smooth curves and think, well, they're pretty smooth. That can't be too very difficult to deal with. But you have to put it in the longer-term perspective of what the climate naturally does during this period in Earth history. So there again we have our 2,000-year temperature record. Here we have what we've observed so far, and now I'll put on the projections, and they look like that. So again, this is 2100, so 100 years is about like that, just out there. And there's about 1.5 degrees, and there's 5 degrees or so. Doesn't sound like much, but look at what ecosystems are used to. Look at the magnitude and rate of change there. This is why we have a really serious problem with many species, many ecosystems trying to cope with this level of change. We're pretty much committed to 2 degrees. So in an ideal world, this is still what has to be coped with, non-trivial. The worst case scenario, which is up at the top, 4 or 5 degrees, is almost hard to imagine. In fact, a particular species, Homo sapiens itself, is going to have trouble adapting to that. And many of us think that this is pretty much a collapse scenario, that even with the technology we have today, we won't be able to survive a temperature rise this fast and this much. So you can imagine with all the wherewithal we have to cope, if we're going to have trouble, what's going to happen to a lot of the other species that we share the planet with. The final thing I want to say is the rates of change. I made a comment earlier on that it's really the rates of change that are important. And we can now make some estimates of what those rates of change are. So if we look at the species extinction rate that we measure now, that's hard to measure, but estimates vary from anywhere from 10 times to 1,000 times greater. Okay, can you hear me there? That's not on. Can you hear me? No. Maybe I'll try to shout. Can you actually hear me around the room? No. Oh, hold on.
So Damien, the sound guy, has gone missing. We were just waiting for him to refresh. So Damien, we're just running out of a bit of puff up here. Can you go back? It's just not coming through. Okay, so what's your suggestion? Go with this one? Okay, we'll give that a try.
Okay, can you hear me now?
Thank you.
I'd like to be able to blame either CSIRO or Telstra for this, but I suspect I can't. Anyway, we're back online. I think, in case anyone missed any of this, what I've done here is put the IPCC projections in orange for 2100 on the same scale as the 2,000-year temperature record. So you can see the magnitude and rate of change that we are facing, we as a species ourselves, but all the other species that inhabit the Earth with us, compared to what we're used to. So it's a massive change in both magnitude and rate. And the comment I made at the end is that if we go to the upper business as usual scenario that we're tracking on now, not only will a lot of other species be in deep trouble, Homo sapiens probably will too. And it'll be very difficult for us to cope with that. The last point I really want to make before I turn it over to people who know a lot more about species and ecosystems than I do is to compare the rates of change, because I showed you earlier on slides past trends, and we can actually back out the rates of how fast the system was changing then compared to now. So species extinctions, anywhere from 10 to 1,000 times. It's hard to estimate that, so the estimates vary. It's certainly more than the background rate, and it could be as much as 100 to 1,000 times. CO2, atmospheric CO2, it's going up about 2 parts per million a year. You see the Mauna Loa curves, they look pretty gentle. It's actually about 100 times the maximum rate during that very steep time when the Earth came out of the last ice age. That looked almost vertical. Well, it's 100 times faster than that. So plants have to cope with that. Ocean has to cope with that because a fair whack of that dissolves in the ocean. And of course that acidifies the ocean as well as contributing to heating it. But the interesting one I think is this. Since 1970, that global average temperature sweeping up is 170 times the background rate. We can't find any time in the past, at least maybe 65 million years ago, when we seem to have an explosion of methane from the ocean floor. Might have been that fast, but for the last 65 million years, it hasn't even been close to this fast. At least in the last 7,000 for sure. And it's moving in the opposite direction. There was a slow cooling trend for about the last 7,000 years. And the last comment is the last time the Earth came out of an ice age was an extremely rapid temperature rise. That was that spike I showed you on the first slide. Today, it's moving now at 20 times faster than that. So we've got a real problem, and that's the background I wanted to give you before you hear from the people who know a lot more about ecosystems and species. Here's the bottom line. Species face climate change at a rate not seen for the past at least a couple of 1 to 2 million years, but as I mentioned, probably not for the past 50 or 60 million years. Something entirely new toward them. And they must try to move through landscapes that are simplified and dominated by humans, and they have to try to cope with and move through oceans that are both much warmer than they were a few hundred years ago, and they're more acidic. So it's at least a double or triple whammy when species have to try to cope. So that's the physical science background. I'll stop at that point, and we'll turn it over to the people who are experts on the species. Thanks very much.